Hi, madam. Shall we start or shall we wait for another 2 to 3 minutes?
We can start
2 3 minutes.
2 3 minutes. After 2 3 minutes we will start, sir. Yeah,
Okay.
9:10 we will start.
Okay. Madam.
We'll start, Payal.
Yeah, we will start. Okay, sir. Shall we
Yeah, we'll
start, sir?
start. Yes, ma'am.
Okay. So very good morning to all of you. I am Dr. Sara K from School of Engineering, Dayanand Sagar University, Bangalore, Conference Chair for the National Conference on Recent Trend in Engineering, scheduled on 3rd and 4th May 2021, organized by the Department of Electronics and Communication Engineering. At the outset, I take this opportunity to welcome Dr. K. N. Murthy, Vice Chancellor, DSU, Dr. Puttamadapa C., Registrar, DSU, Dr. A. Srinivas, Dean SOE, DSU, Dr. M. K. Banga, Dean Research, DSU, Dean of other schools of DSU, Dr. Webber, Chairman, Department of ECE, and Chairman of other departments. I also extend a warm welcome to all the keynote speakers, faculties, and participants to this conference, NCRT 2021. Amid the present pandemic situation, things are getting tough day by day, but time doesn't stop, and so do we. Hence, we have arranged this virtual conference to keep things moving. The engineering world is an ever changing environment with the new technologies and development. The rise of Internet of Things, embedded systems, photonics, virtual reality, artificial intelligence, and 3D printing are set to dominate the industry in the next coming years. NCRT 2021 is a forum for engineering students, research scholars, and delegates to present their research work as well as exchange knowledge on recent trends and development in engineering. The conference includes invited lectures from eminent academicians, industrial experts, and paper presentation by the participants. All the accepted paper will be published in a conference proceeding with ISBN number and in UGC approved journal. The main objective of this conference is to disseminate latest research findings and technologies achievements in the field of electronics communication, mechanical engineering, computer science, and aerospace engineering. I would like to introduce my colleague Dr. Rajeshri Anna Narendra and Mrs. Anna Marin George of EC Department, DSU, Bangalore, who are also the organizing chairs of the conference. We are glad that we have received more than 70 papers for the conference, and the participants will present their paper virtually today and tomorrow in 6 parallel tracks. Apart from the paper presentation tracks, 5 keynote talks have been arranged for today and tomorrow on the latest topic of research such as nanotechnology, photonics, virtual reality, optics, and so on. With this note, we inaugurate the two-day national conference on recent trends in engineering, NCRT 2021. And now I request our chairman, Dr. Vaibhav AM, to address the participant.
Okay. Thank you, Payal madam. Thank you, Rajeshri madam. And thank you, our Anna madam, for putting these efforts in bringing to this level NCRT 2070. This platforms gives us all the presenters and all the researchers and the research scholars, those who are pursuing the PhDs, those who had completed the PhD, to showcase their research work. And going ahead, our approach will be most, as you see, in National Education Policy 2020. The approach in the National Education Policy 2020 is interdisciplinary. We must emphasize on interdisciplinary approach. And my dear students, all and participants, all you are aware that electronics is the most suitable branch for the interdisciplinary activities, or the work we are doing in the electronics domain is mostly suitable for the interdisciplinary. If you take any application, since morning you wake up till you go to the bed, you will find some or the other way electronics embedded into it, some or the other way. So we have to emphasize mostly onto the, and that is what you had done in the papers that we had seen, that you had submitted in this conference, are mostly on mostly emphasizing on the interdisciplinary approaches. This type of the conferences also help us in building the networks. Like we have eminent speakers. You please note down their addresses. They will help you in guiding you and doing your research further, and to carry out the research further. So any type of a guidance from any senior and from our eminent speakers, it will be always be helpful for our students as for and the budding researcher and who has already completed the research, because research is such a thing which cannot we cannot say that it is I had completed my research and this is the end of my research. It is a continuous process. It is a continuous process, and in this continuous process, we also also need to seek the guidance from people, those who know the people, those who knows the subject, and we can find a guru, or we can find a guru in even in a kid, and even in a kid, or even in a highly professional people also. So keeping this in the mind, apart from this thing, we have to also see that we need to our wishes, our honorable vice chancellor vision is there to build a creativity, communication, critical thinking, and collaboration concept into the student. This will lead to further into good research. This will also build the confidence of a student. So my dear student and the participant, those who had submitted their papers, make this opportunity to interact with the speaker, to listen all the tracks. You don't know whether, as I told you again, that it is interdisciplinary approach. We don't know that which knowledge will be applicable. So try to attend all the tracks, see that and if you have any question, please don't hesitate. Please never hesitate to ask the questions. You must ask the question and never hesitate for asking the question. You must see that all the tracks you are attending carefully, and you are listening to the speakers very carefully. Make the note of the reason, what are the activities that have been done into this NCRT 2021. My dear student, you had done a good, my dear students and researchers, you had done a good project. So it is a nice place to showcase your talent. And whenever somebody asks question, don't take it in as you are some of you might be presenting for the first time. So don't take it as something like a critics or something critical. Take it as in a very positive way and try to improve on that. And try to improve on try to improve on the suggestions given by the panel member. There will be session chairs where you will be presenting the papers, and whenever some comments come, try to take it in positive and try to see that how you can improve in that. How can you improve into that in your research activities? So basically, during this pandemic, it's very difficult. We are going through a very difficult phase. We had never seen such type of situations earlier. And it is a good and it is a bad also. good in the sense good in the sense we are able to listen to good speakers. It's on online mode, which may be difficult for a person to travel if it is in the offline mode. We have speakers, we know Shrikant sir, they are very learned people. It's an opportunity to listen to them. Otherwise, it could have been difficult to call them, and they were busy in their activities. With their schedules, they are busy. Vinod sir is working in the industry; he's busy, so it may be difficult for him to travel. But this pandemic can also give this type of opportunities where we can listen to this eminent speaker by sitting at home. That is the advantage of the technology. By sitting at home, we are able to listen to them. There's no need of travel. This is one or two advantages, but there are many disadvantages also. But when there is so much negativity spread, we must look into something which is very positive. And the positive thing is that we are arranging this NCRT, and we have a very eminent speaker here. Shrikant sir is quite experienced person. Vinod Kumar sir is also experienced. They will be speaking about the research activities they are doing. We have a very nice speakers in 2 days. We have who has a rich industrial experience. They will help us in sharing their knowledge, and we have to gain the knowledge from them. In this type of the situation where the so much problems are there, we also must think that some projects which must be helpful for a societal need. There may be some project which should be helpful for societal need. There is shortage of oxygen, there is shortage of vaccine, there is shortage of medicines. We need to see, can we work in that direction also? Can we go do our research in that direction? We have to look into that way also. We have to look in that way also. And having said that, I thank Vinod Kumar sir for joining as a keynote speaker, and Shrikant sir also. Today we have 2 keynote speeches with a parallel session, which the organizers will keep you updating. I must be thankful to our Mohammad Imtiaz sir, who had helped us in arranging this. Who had helped us in arranging this Zoom link for this conferences. So all of us had come together, and we had all put the efforts. We had all put the efforts to make this a conference successful. We had put my dear students and my dear presenters, those who are present in the paper today, make the best use of this opportunity, because there are a lot of efforts gone. In arranging these conferences, and in spite of their busy schedule, Mr. Vinod and Mr. Shrikant are there to share their knowledge. We should always be grateful for them, and we must listen to them and their vision, their research activities that they are doing. Having said that, I say that you should attend all the tracks parallelly, which will be going on parallelly, and try to gain most of the knowledge from this thing. Thank you, Sarah ma'am. Thank you, Payal ma'am. It's over to you.
Thank you, sir. Now, keynote lecture will begin. First keynote lecture is on importance of nanotechnology in energy sector by Dr. J. Vinod Kumar. Now, let me introduce the first invited speaker, Dr. J. Vinod Kumar from CECRI, CSIR Chennai. Dr. Vinod Kumar J is currently serving as a research associate in Central Electrochemical Research Institute, Council of Scientific and Industrial Research, Chennai. He received the BE from the Anna University, Chennai, ME from VIT University, Vellore, and PhD from Sinvista IPN, Mexico City. So Dr. Vinod was awarded with SNI 1 prestigious award from National Council of Science and Technology. He won the highest paid postdoctoral fellowship from UNAME. He got National Council of Science and Technology doctoral fellowship for 4 years. He is a gold medalist in PhD with nanotechnology as his area research interest. Dr. Vinod Kumar is a member of Project Evaluation Committee, National Science Center, Poland, and National Council of Science and Technology, Mexico. He has published about 40 papers in reputed journals and conferences. With these few words, I request Dr. J. Vinod Kumar to take over the session. Now, Dr. J. Vinod Kumar, now you start your speech.
Thank you, Dr. Sarah, for such a nice introduction. Thank you so much. Dr. Sarah, can you able to see my screen?
Yes, sir. It's visible.
Yes, sir, it's visible. It's visible.
Yeah, thank you. Good morning, everyone. This is Vinod Kumar from Central Electrochemical Research Institute. I am going to give a talk on importance of nanotechnology in energy sector. And what is nanotechnology? Nano is one of the most frequently used words in the science and technology in recent times. And the word nano, it is actually a Greek word which means small or dwarf. And in simple words, we can say like working on a 1 billionth of a meter, which is 10 power minus 9. Here, in the bottom of there is one microscopic image, which you can see, which is of 10,000 nanometer wide. This is our human hair. And what is nanotechnology? In simple definition, we can say like a field of applied science focused on design, formation, and identification and using it for an applications of materials and devices on the nanoscale. Nanoscale in the sense in any one dimension of a material which will be varying between 1 to 100 nanometers. And these nanomaterials can occur naturally or it can be produced by human activity or by following organized method on purpose. With a certain objective, we can design our own nanomaterial. For example, naturally occurring nanomaterials are such as forest fires, volcanic ash, and viruses which are already spreading. Those are all in the order of nanometers. And accidentally what is found is like cooking smoke, diesel exhaust, welding fumes, those are, and sand blasting, industrial pollutants, and those things will be of nanometer size. And intentionally, when we want to produce some nanomaterials, and we can produce like metals, quantum dots, buckyballs, sunscreen pigments, and nanocapsules. And when we intentionally prepare these materials and we use it for certain applications, then the term is broadly classified as nanotechnology. For example, in the first image, you can see like nanopowders. And in the second one, which is called as nanotubes. Basically, these are like carbon nanotubes, which are arranged in C6 format. And the next image is like a buckyball, which is called as C60. And we can make nanomaterials by two approaches. One is top-down approach, another one is bottom-up approach. In the case of top-down approach, etching a block of material down to the desired shape. In the sense, we can take one big material, for example, bulk, and that can be cut into several smaller objects to achieve the desired size. For example, these things are mainly used in the chips and processors. This is the top-down approach, which is being used in electrical and electronics. Another thing is bottom-up approach. Here, materials are built by atoms. And for example, C60 carbon nanotubes and quantum dots are following the bottom-up approach. When these materials are synthesized, these are arranged one by one by arranging the atoms by chemical vapor deposition or pulse vapor deposition, and such kind of techniques are bottom-up approach. For example, on the right-hand side, you can see right second one. These are multi-walled nanotubes, and which is in ball shape is called C60 buckyballs. And this one is like a core shell structure where we can see the multiple atoms are formed like a core shell inside one material, and the outside surface you can see of different material. This is called building materials atom by atom as per our requirement. This is called bottom-up approach of making nanomaterials. And what is happening at nanometer scale and why we are really going for it. And what happens is, for example, on the right side image, you can see a bulk material, which is of size 1 centimeter by 1 centimeter, where its surface area is only 6 centimeter per square. In that case, when we use this bulk material for a certain application, the surface which is going to react the reactivity will be very less. Whereas when we divide this material or cut into several objects of micrometer, for example, 1 millimeter cubes, and the surface which is going to react with certain conditions will be more. The active surface area is much more better than the bulk. When we reduce the size further from cubes to powders, when the size goes like 1 nanometer cubes, and it becomes highly reactive, and it gives enhancement in several properties, such as increase in the thermal stability of materials. It improves the mechanical strength or densification, and it improves the electrical conductivity of materials. And another one, in the case of optical properties, it improves the transmittance and reflectance and etc. And by varying this size between 1 nanometer to 100 nanometer, the properties can be tuned according to our application. For example, when we improve the conductivity, electrical conductivity of a nanomaterial, those things can be easily used as a channel material between source and drain, which can be employed in transistors. For example, in the meantime, when we want to go for a highly non-conductive material, a highly resistive material, those things will be helpful in making water purifiers, where we are looking for less conductive materials. And again, instead of electrical conductivity, if you are going for ionic conductivity improvements, if we go for nano size, and these things can be used for batteries as a solid state batteries. And when we play several parameters like optical and electrical properties together, and those things can those things can be used for solar cells, where the optical transmittance as well as the electrical properties are important for certain applications. Hence, we can say that there is enhancement in the properties at the nanometer scale than the bulk materials. And these are the nanotechnology is a multidisciplinary area, and this can be employed in several applications. For example, this can be used from agriculture, food industry, water purification, and material science industries, electronics, optical engineering, which can be used for LEDs and laser applications, and cosmetics, pharmaceutical industries, biotechnology, textile industries, as well as energy storage. Let me go one by one. And in the case of agriculture, among the various nanomaterials, the metals and metal oxide nanoparticles with certain sizes, morphologies, which will give enhanced properties like chemical properties, and this will give like the degradation, agrochemical degradation, as well as soil remediation. And these nanomaterials, when we use as fertilizers, and this will increase the dispersion as well as wettability for agricultural formations. And what really it does is it will increase the productivity of agriculture, and it will improve the quality of the soil instead of spoiling it when we use like the normal fertilizers. And another one is it stimulates the plant growth. Instead of having a plant growth in 6 months, we can have productivity in 4 months itself. And another one is by having a certain sensors which can be implemented on the soil, we can monitor what is the water level required, and how much water need to be saved, and those things can be easily monitored by designing some nano sensors, and continuously this can be monitored. And another thing is food industries. Nanoscale food additives have the potential to extend the product shelf life and improve the texture, flavor, and nutrient compositions. For example, a certain milk product or any milk product which is like validity of just 7 days, when we use certain antimicrobial agents, these things can be the product shelf life can be extended like twice. And when we use some additives to detect the food pathogens and provide functions like food quality indicators, this will maintain the food quality. And another thing is, and there are some new sensors that are designed recently, and this can identify is there any contamination in the food, and this can be examined within a fraction of seconds. And another important application of nanotechnology is in the water treatment. Nowadays, the water deficiency is a major global problem. Unfortunately, 1 billion people do not have access to the safe drinking water, and this is being increasing day by day. And the study of regions that suffer water shortage around the world reveal that most of the areas in the developing countries are having such a huge water crisis. And scientists and researchers believe that nanotechnology could be a possible way to tackle these challenges to get the clean water for the people. And nanotechnology will offer an inexpensive and efficient treatment of wastewater in order to convert that as a drinking water. And the most frequently used nanomaterials for water purification is nano-sized titanium dioxide and zinc oxide and fullerene membranes as a filter. And another one, and this work was done by us. And in the case of wastewater treatment, for example, mosquito is one among the dangerous insect around the world. The thing is that in order to eliminate the production of mosquitoes, usually there are several insecticides like scourge, anvil, permethrin, malathion, parathion, DDT, and temefos are used on the water bodies in order to reduce the mosquitoes growth. If we have like mosquitoes growth, it leads to several diseases like chikungunya, Zika fever, and West Nile virus, and several fevers, right? So World Health Organization recommended the countries to use these insecticides less than 1 milligram per ml. Unfortunately, the government doesn't follow these conditions, and they will use excess amount of pesticides or insecticides just for the growth of mosquitoes. And thing is that the water becomes contaminated by using these pesticides, and under the influence of sunlight, these chemicals will convert to another byproducts which can be easily damage the DNA of our human lymphocytes for even low concentrations of such pesticides. Hence, such kind of water bodies like which are in the lands and ponds has to be treated in an effective way, so that the toxic temefos or any other insecticide supposed to be eliminated from the water, and it should be safe for the humankind. And here we have used like a nanoroses of zinc oxide for the elimination of pesticide from the water. What here you can see, it contains like a garland structure which contains several roses of zinc oxide, and these are highly reactive, which is having high surface area. When under the influence of sunlight, these zinc oxide will act as a photocatalyst, and it will reduce the toxic compounds and convert that to pure H2O, which are then the final product of water is safe to drink. And another important application of nanotechnology is in the medicine area. The formation of nanosized system has special importance because it influences some pharmacokinetic and pharmacodynamic characteristics. In fact, the nanosized drugs, due to large surface area, produces superior abilities and performance such as enhanced solubility and rate of dissolution, oral bioavailability, and rapid action. And this will require only low dosages, and the patient to patient variability will be very less. The another important application of nanotechnology in medicine is targeted drug delivery, especially in cancer treatment. For example, if some people are having lung cancer or breast cancer, whatever it is, when we use like carbon-based medicines, that particular instead of injecting and throughout the body, if we inject on a particular place, this nanomaterials will go and target only the place where it is infected. Only those cells are particularly targeted, and it will destroy those cells, and the treatment will be much more efficient than the current one. And another important application of nanotechnology is in the field of energy. Nowadays, the major energy sources used to fulfill the human requirements and activities are fossil and mineral fuels, nuclear energy, and hydroelectric sources. And these are so expensive and also causes several damages to the ecology and causes several things such as global warming, ozone layer depletion, biosphere and geosphere destruction, ecological devastation. So the importance of nanotechnology in the last few decades has provided several tools for protecting our environment from these things, that too in a cost-effective and efficient way. And presently, nanomaterials employ new potential in the production and development of efficient, inexpensive, and can be used for the conventional as well as renewable energy production itself by using the extraordinary properties of nanosized materials. And also this technology provides the several solutions for the better production of energy. And this technology is used in the all part of energy sector, such as energy generation, storage, transmittance, distribution, as well as in the management of energy. Let's see one by one. And by using the nano-coated wear-resistant drill probes in the petroleum technology, it will improve the lifespan of the drill probes, and also it improves the efficiency, and also it is cost effective. The another thing is for windmills, when we use the lighter and rugged rotor blades with nanomaterial based things, and it will be like wear and corrosion resistance for mechanically stressed components. And when different morphologies of organic semiconductor mixtures are used for enhancing the solar cell efficiency. And generally, these kind of nanomaterials are used like a window layer for several solar cells. And the improvement in the electrical conductivity of materials at nanoscale has meant that they are employed in many ways, such as electric cables, power lines, batteries, supercapacitors, nanosensor devices, and power electric components that can be used for several applications. And in our laboratory, we are mainly working with energy storage. The energy, as I said earlier, energy can be divided into several sections like generation, storage, transmission, distribution, and management. We are mainly working with the storage section. And in particular, we are working on lithium-ion batteries. Let me start with a brief idea. The word battery. is borrowed from a Latin word called batter, and which is borrowed again from French, which means strike. Though this is not having any relation, they named it. And another thing is, in general, we can define batteries as electrochemical device which stores electrical energy as chemical energy in electrodes. And the batteries can be classified into two types. One is primary, another one is secondary. Primary batteries are energy storage device which can be used only once. For example, when we use that in watches or something, wall clocks, those things can be used once and they can be discarded. Whereas secondary batteries are ones which can be charged and recharged and go to several cycles, which can be used multiple times. And lithium-ion batteries. There is no day-to-day life without lithium batteries. For example, these are used in portable electronics, buildings, pharmaceutical, as well as in transportation. In the case of portable electronics, whatever we use, all the electronic gadgets such as laptops, tablets, cell phones, digital cameras, watches, power banks, flashlights, Bluetooth speakers, and audio phones, everywhere the lithium-ion batteries plays a vital role. As well as at homes and offices, we use it as a power backups. And in the case of medicine industries, it is being used in several biomedical instruments, as well as hearing aids, and also mainly in heart pacemakers. And in recent times, we can see the transportation like cars, bikes, and buses are being used with lithium-ion batteries to eliminate the pollution from this world and to reduce the CO2 emission. And in the past 3 years, more than 53,000 articles were published in the indexed journal based on lithium-ion batteries alone. And more importantly, these are being focused towards electric and hybrid vehicles. It's for having a special focus towards the environment. And this lithium-ion battery technology is mainly for limiting the carbon dioxide emissions and slowing down the climate change. Among the various rechargeable batteries, lithium-ion batteries are ranked on the top for its special characteristics such as low self-discharge rate, high energy density, and also this is a lightweight material. Low self-discharge rate in the sense, for example, we are charging a mobile for 100%. Without using, you are keeping it in the shelf for like 5 days or something. In that case, the lithium-ion battery will lose its charge just like only 3 to 5%, whereas other materials like sodium-ion batteries, potassium-ion batteries, or magnesium-ion batteries will have a high self-discharge rate. When lithium loses only 3%, whereas the other materials will lose like 10 to 15% of discharge rate. And another thing is energy density, high energy density. Amount of energy that is being used for several applications can be much higher when in lithium-ion batteries when compared to other batteries. Another thing is which lies on the top in the periodic table, and it is a lightweight material. And the basic lithium-ion battery components and mechanism are shown here. Basically, the battery consists of cathode, anode, and an electrolyte. In the case of lithium-ion batteries, the cathode materials will be of lithium oxide materials. The anode will be like graphite, and the electrolyte will be like LiF36, lithium hexafluorophosphate in ethylene carbonate. Let me explain you the charging. During charge, what happens is on the left hand side, you can see the remotes, right? This is the lithium-ion battery, and during charging, the lithium ions from the cathode will move via the electrolyte, and it will go and occupy the sites which is in the anode, which is of graphite. These lithium ions will penetrate through the electrolyte and occupy here. And during discharge, the lithium ions will move back to the original location or whatever the vacant sites available in the cathode side. That is how the lithium ions will move from cathode to anode and anode to cathode. When it moves from cathode to anode, it is charging. When it moves from anode to cathode, it is discharging. That is when we are using it for a certain application, such as during transportation or when we are using it, where there is current generation. And coming to the cathode material preparation, basically, as I said, lithium metal oxides are used as a cathode materials. The materials such as lithium cobalt oxide, lithium manganese oxide, lithium iron phosphate, and lithium nickel cobalt manganese oxide. Currently, the last one, lithium nickel copper manganese oxide, is the one which is currently being used in all the electronic gadgets. The thing is, the lithium copper oxide is expensive and the availability of copper is very less. We are going for another composite such as combination of materials like NCM, nickel, cobalt, and manganese in replacing this cobalt. And these active materials, the cathode active materials, can be prepared by following several methods. Among one, the easiest method is like co-precipitation or combustion method. Here, generally, what they do is they will take all the precursors, the starting materials of lithium, nickel, copper, manganese together, and they will mix it with a solvent, and they will produce a salt, and it will be calcinated for certain hours at certain degrees, and finally we will be obtaining powders. And, for example, after calcination of 900 degrees for 24 hours or something, we will have materials like NCM oxides of different shapes. For example, here these are all said to be a layered structures of NCM. By playing several parameters like grinding condition, calcination temperatures, we can modify the shape, size, and the particle size distribution at nano level. This will enhance the lithium-ion battery performance, like improvement in capacity and improvement in thermal stability and improvement in the cycle rate. And yeah. After the preparation of this material, and we need to fabricate a slurry to make a battery. For example, these cathode materials are mixed with binder and solvent to make it like a paint, and that will be coated on aluminum foil, and it will be dried like between 95 to 120 degrees and form like a uniform coating. And this will be used as a cathode material for a battery. And coming to the anode materials, the most commonly used is carbon nanotubes. Graphite, diamond, nanotubes, or graphene can be used as an anode material. And coming to the carbon nanotubes, and graphite is a commonly used bulk material. However, since we are interested in nanomaterials, in order to have a higher efficiency, we are going for carbon nanotubes and graphene. Let me give you a small introduction about carbon nanotubes. And CNT is carbon nanotube is a tubular form of carbon with diameter as small as 1 nanometer. And these are of two types. One is single walled carbon nanotubes, and another one is multi-walled nanotubes. And these are like strongest and most flexible molecular material, and this is having high mechanical strength. The Young's modulus of over 1 terapascal and 70 gigapascal for aluminum, which is better than aluminum. And this is having maximum strain of 10%, and thermal conductivity is around 3000 watts per millikelvin. and the electrical conductivity is 6 times better than copper, and sorry, 6 orders of magnitude higher than copper, and this can be used as a metallic or semiconducting material, depends on the chirality. Chirality in the sense the how the carbon atoms are arranged in a nanotube. And these carbon nanotubes can be functionalized and can be used for several applications as well. And the method of preparation of carbon nanotubes is of there are several methods. However, the most commonly used is arc discharge, laser ablation, and chemical vapor deposition. Here we will have a carbon source by applying, in the case of arc discharge, we'll have a carbon source from graphite electrodes, and by applying a arc discharge, we will produce carbon nanotubes up to 50 microns of size. In the case of laser ablation, the pulsed laser will vaporize the graphite target, and the carbon atoms are ejected from the target, and nanotubes will start arranging themselves inside the organ atmosphere, and carbon nanotubes are formed. Here in the right bottom side, you can see how the nanotubes are vertically arranged, and this can be used for field emitters as well. And coming to the another kind of anode material is graphene. A single layer of graphite is called as graphene, and this can be synthesized by CVD, exfoliation, or Hammers method. And this graphene is having excellent electrical conductivity, which is of 2000 Siemens per centimeter square, and this is having high specific surface area, and this is having excellent thermal and as well as mechanical properties, and these are mainly considered for lithium-ion batteries. And how we are going to make the anode material for lithium-ion batteries. And generally, instead of going for carbon nanotubes alone or graphene alone, we usually mix carbon nanotubes and graphene together and make it as a nanocomposite by mixing it with CMC, carbon methyl cellulose, and water. We will make it as a slurry, and we will form a coating on copper foil, and it will be dried, and that coating will be used as a anode material. Let's see how the fabrication is done. For example, let's consider a coin cell. Here the top terminal is positive, and below next to that the cathode will be placed, which is lithium, nickel, manganese, cobalt oxide. As I said earlier, this is a separator where the electrolyte will be poured here, and to top of which we will place the anode material, the carbon, either CNTs or graphene or together as a composite will place there, and over which there will be a spring just for sealing purpose, or over which the bottom terminal, which is a negative terminal, and these, by following this order, the material will be crimped and formed as a battery as shown on the right hand side. And this is what said to be a coin cell. And what is happening really when we use nano-sized material in the electrodes? Thing is that there is an increase in surface area, and it provides a short diffusion path where the movement of lithium ions will be faster as the path is smaller. And another thing is, since at the nano level, the structures can be formed of like rods, trigonal, tetragonal, plates, dots, and spheres. This will give a room for more number of sites for lithium ions for storage. What it does is it will improve the capacity, it will improve the thermal stability, and also it increases the cycling rate. For example, improve capacity in the sense, when we use bulk lithium materials, the capacity will be like around 140 milliamp hour per gram. Whereas when we go for nano materials, the capacity will be increased up to 200 milliamp hour per gram. And improve thermal stability in the sense, usually the thermal stability lasts up to 280 degrees. Whereas when we go for nano materials, the thermal stability increased up to 300 or 320. And this provides the excellent cycling. For example, if the bulk material gives like 1000 cycles, the nanomaterials, when we use nanomaterials, the cycling rate will be improved by twice or thrice. And coming to the conclusion, nanotechnology advances are used in disease treatment such as cancer and these things. And nanotechnology is effectively used in batteries and solar cells. And this will nanotechnology will leads to improvement in manufacturing that allow for durable, lightweight, and efficient production tools. And nanotechnology can be used in multidisciplinary area. And I'd like to pay some acknowledgement. I would like to thank CSIR 60 for research funding, and I'd like to thank Organizing and Scientific Advisory Committee of NCRT 2021, and I especially thank Mr. Mayank Chakravarti, our AMR, for referring to this conference. And these are some of the references from where I took some data. Thank you so much.
Thank you, Vinod sir.
Please let me know.
Thank you, Vinod sir. It was quite interesting, and
Yeah.
you thoroughly enjoyed your lecture.
Thank you, Vinod sir, for informative presentation on nanotechnology, use of nanotechnology in agriculture, energy, and water, and all. Thank you so much. Now I am hand over the session to Dr. Rajeshri Narendra. She will introduce next speaker, keynote speaker. Ma'am, Rajeshri ma'am.
Yeah, thank you, Dr. Sarah. Good morning, everyone. The next keynote lecture is on photonic sensors by Dr. P.C. Srikanth. Let me introduce Sir. He is a professor at MCE Hassan. Dr. P.C. Srikanth had his schooling in Hassan and graduated in Electronics and Communication Engineering in 1987 from Malnad College of Engineering, Hassan, Karnataka, securing a first class with distinction. He has completed his MTech degree in 1996 from IIT Kanpur in the area of lasers and obtained his PhD from VTU Belgaum. He worked in the Applied Photonics Lab at IISc Bangalore during his PhD. Starting as a lecturer in 1987, he became assistant professor in 1999, professor in 2011 at Malnad College of Engineering, Hassan. He has a deep involvement in optical networks and was awarded as Top 100 Engineers 2011 by International Biographical Center, St. Thomas Place, Great Britain. He was selected for Marquis Who's Who in Science and Engineering in 2011-12 and also in 2016 and 17. This is awarded by New Providence, New Jersey, USA. He received Best Paper Award for the following papers: Modeling of Photonic Crystal Ring Resonator Temperature Sensor during 2014, a novel quantum dot automata-based design for multiplexers during 2015, detection of fluoride-contaminated water in dental applications during 2015 at in various international conferences. He has been awarded as outstanding scientist in the field of photonics by Venus International Foundation card on 19th December 2015. In 2018, he received Albert Nelson Marquis Lifetime Achievement Award for Marquis Who's Who in Science and Engineering, New Providence, New Jersey, USA. His research areas includes optical communication and networks, photonic band gap crystals, wireless networks, lasers, and quantum electronics. He has guided and is guiding more than 100 BE, MTech, and PhD students. He has so far published 150 papers in national and international journals and conferences. He has attended many national conferences in India and abroad and has chaired many technical sessions. He has also organized many international conferences and workshops. He has also given many keynote and invited talks in international conferences and workshops. So far, he has received 14 awards, and many awards and laurels run into volumes. Dr. P.C. Srikanth is a senior member in IEEE USA, life member IST. Currently, he is vice chairman at IEEE Photonic Society, Karnataka. Sir, now I hand over the platform to you, sir.
Hello, Shrikant sir.
Imtiaz sir, can you please make him co-host?
Yeah, it's there, madam. Shrikant sir is co-host.
Oh,
Thank you, Imtiaz sir.
okay. Thank you. Thank you, sir.
Dr. Shrikant sir, welcome, sir.
Hello, Shrikant sir. Shrikant sir is there.
1 minute, some technical problem is there, ma'am. 1 second, 1 second.
Yeah.
No problem, sir.
One second, I'm calling. Sir.
He's online. I think some technical issue at.
Yes, something. I'm calling you.
Imtiaz sir, what is the problem?
Sir is having some technical problem. Shrikant sir, he's once again logging now.
Oh,
Please,
okay, okay. He's logging.
share with us,
Okay.
participants.
Okay.
Because of some unstable internet connection, he
Okay.
will be just logging in 2 minutes.
Okay, sir. Sure, sir.
Shrikant sir.
He's yet to join in, I think, sir.
Sir, unmute yourself. Sir, unmute. Shrikant sir.
But yeah, now I'm unmuted, no?
Yeah. Now it's coming.
No, yeah. Yeah, I am on the screen now. I am on the screen. Okay.
Welcome, sir.
Really good.
Morning, Shrikant sir.
Yeah, I'm on the line.
Yeah, audible, sir. Thank you, sir. Thank you, Imtiaz sir. You're audible, sir. You're audible. You're audible, sir.
Sir, you can start the session, sir.
You can
Audible?
start. Yeah, you're audible.
Yeah, 1 minute. I'm just sharing my screen.
Okay, sure, sir.
Sir, you first open the PPT, sir, and then you can share that PPT. Shrikant sir, you can open the PPT. First, you open the PPT, and then you give the sharing option, sir. Because now your screen is visible, but Sir, no, don't click that, sir. You just, sir, you just open the PPT and then it will do the sharing. Sir, you come out of the sharing option, sir. Now you open the PPT, sir. First, you open the PPT. Sir, I'm audible. Sir, else you send me the PPT, I will share it, sir, from here. Sir, Shrikant, sir?
Shall I send the PowerPoint?
Yeah, you send it to me, I will share it from here, sir.
Yeah, 1 minute.
On email, you send it, sir. Sir, which email ID you had sent, sir? Sir? Which is the email ID that you had sent it, sir?
I think he's
Shrikant, sir,
sending.
which email ID you had sent it, sir? You sent it to chairman-ec@dsu.edu.in. Sir, you had sent it to which email ID? Shrikant, sir?
I think some internet issue.
No.
Hello, Vaibhav? Hello?
Sir, which email ID you had sent, sir? Yeah, it's audible, sir. Sir, which email you had sent it?
Vaibhav at DSU.
By one. Okay, sir.
Vaibhav, you have received the mail?
Yes, sir. I'm opening it, sir. I got it. I downloaded it. Just 2 minutes, I'm sharing it.
No problem. Because my talk is scheduled, I think, 10:25.
Yes, sir. Just, sir, it's opening, sir. Just give me 1 second. It's done. One second. Sir, you are able to see it, sir? Hello?
Yeah, I can see your screen. That's all. Not PowerPoint.
Yes.
You open PowerPoint.
And, oh, 1 second.
Third and fourth minute.
1 second. Sir, you are able to see now?
Yes, sir. Yes, sir. We are able
Hello?
to see. Yes, sir.
Sorry, participant, for some technical glitch. We'll start.
Yeah, it's visible, sir.
Shrikant, sir, it's visible now.
Hello? Vaibhav?
Yeah.
Hello,
Yeah,
sir.
Yes, sir.
You can start, sir.
Yeah, will
Visible.
you go for this one mode? What is that?
Slide mode.
Slide mode. Yeah, okay.
Yes.
Fine.
So can I start my talk?
Sure, sir.
So, okay. I would, this is really a very good gesture from Dayanand Sagar University. They are hosting a very big national conference. Thanks to Vice Chancellor K. Palasubramaniamurthy, Vice Chancellor, Management of Dayanand Sagar University, Chairman Dr. Vaibhav Meshram, Dr. Sara, and my dear colleagues and my dear participants and listeners of my talk. So once again, I thank all of you having been given a chance to give my invited talk in the keynote talk in this international conference. First of all, because of some technical sag, we are not able to connect to each other. Now I'll start with the things. I think Vaibhav is on. Who is changing the slide? Vaibhav?
Yes, sir.
I'm changing the
Vaibhav?
slide, sir. I'm changing.
Yes, sir.
Yeah, okay, you can start. Okay, now I would like to give some outline about it. We go to the previous, okay, okay, it's okay. So first of all, I'd like to give some introduction. Next slide. So I would like to give some introduction about technology, but here it was new technology, but still a lot of things to happen in this one. Complications. And also I'd like to give what is photonic crystal ring resonator. Design and modeling of PCRR, temperature, FTDD method, simulation result, analysis of fluoride contents in water using PBG sensor, and finally conclusion. Go to the next slide, Dr. Vaibhav. Next. Yeah, looking at this one, this butterfly, you can see what is photonic band gap. I'm just sharing with you. You see that color on the butterfly. That means to say that the colors perceived by eye is nothing but change in refractive index of the butterfly wings. What I tell you, it's a periodic structure. So what will happen? It is just like a band reject filter in our frequency domains. Low frequency components are passed, high frequency components are cut off. Only the middle high frequency are also passed. Only the mid range is stopped. So in this photonic band gap, when the mid range is stopped, the wavelength is stopped, reflection will occur. Because of the reflection, we are going to see the color on the wings of the butterfly, as well as like some peacock or parrot, colors of the wings of the parrot, like that. It's a naturally occurring phenomena. So we have explored out of it how we can manufacture. Okay, photonic band gap crystal is, yeah, okay, good. Photonic band gap crystal is a structure that can manipulate the beams of light the same way semiconductor can control the electric current. Okay, and so semiconductor connector cannot support electrons of energy lying in the electronic band gap. Similarly, photonic crystal cannot support photons lying in the photonic band gap. There is electronic band gap. I already told photonic band gap. So photonic band gap, once again, I am telling you, because of reflection we are going to get, because certain bands are not passed. That's the reason why we call it as photonic band gap. Okay. So definitely there are some things which is available. Optical fiber, you know that one. It is a form of light from one end and you can see the light from another. It also you can have you can send the light from one end and you can receive the light from other end. So the thing last one which I am going to discuss is photonic crystal waveguide, the last one. Okay, so where we have simulated, and I'll show some of the results also. Okay, next. 1 second. There is some power failure here. Okay. Hello. 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 Am I audible?
Yeah, we are able to hear you, sir, but a little bit voice is breaking.
So, once again, there's a problem with the audio. Once again, I'll come back. Once again, wait for one minute. Sorry. Vaibhav. Hello, Vaibhav.
Yeah, hello, sir. I'm able to. We are able to hear you, sir. Sir. Hello, sir. Sir, we are able to hear you, sir. Hello, sir. Hello, sir. Okay, okay. No, no, sir, you're the host. Okay, I will ask.
So please unmute my audio and video. No, now it is unmuted. Okay, now you are hearing it.
Yes, sir. Yes, sir.
But video also it's not unmuted.
No, no, sir, I'm anyway sharing the slide.
Okay. So okay, now we will go to the next slide.
Now video is also coming. No problem. Video
okay.
audio both are on.
Yeah, next slide. So then direct equation will get large in size, and also the most important thing is there will not be any what you call 90 degrees bend is not possible. Okay, 90 degrees, right? Hello, audible?
Yeah, you are audible, sir. You are audible.
Clarity is there. Voice clarity is there. Vaibhav?
Yes, sir. You are audible.
Yes, sir. Everything is fine. Yes, sir. You speak, sir.
Everything is fine. You proceed. Audible, sir.
Okay. Then photonic crystallization. Right, we cannot bend 90 degrees because light will not be confined into the wavelength. It will escape out of it. Okay, next. Vaibhav, next.
Yes.
Next slide. Blank is coming.
Yes, blank one.
Hello. Yeah, you can see. So what we could do is it is just like to understand. There will be optical source and optical detector.
Sir, your voice is breaking. Sir, your voice is breaking.
On camera.
Your voice is breaking, sir.
Sir, better to switch off video, sir.
Yes. So you can switch off the video, sir. Hello. Hello, sir. You're audible, sir, now. Shrikant, sir. Sir, you're not audible, sir. Shrikant, sir. Sir, you're not audible, sir.
Yes, sir. Yes, sir. Audible, audible. Sir, voice is coming, no?
Yes, yes. Audible, sir.
Hello?
Yes, sir. Sir, you're audible, sir. Please speak.
Vaibhav?
Hello, sir.
Yeah, you please unmute. Unmute.
Sir, we are able to hear you, sir.
But you are able to hear you from my laptop. Laptop, there is no.
Sir, we are able to hear you, sir. You speak, sir.
You are able to hear.
Yes, sir. Yes, sir. Yes, sir. No problem. You speak, sir. Hello, sir. We are not able to hear you, sir.
Okay, there is optical.
Sir, you please unmute yourself, sir. Shrikant, sir.
So now I'm audible. Hello, Sarah.
Yes, sir. You're
Am I
audible, sir.
Yeah, okay. So now we can look at this one. Just a minute. Now I'll start. Second. Professor Vaibhav. Vaibhav. Vaibhav.
Yes, sir. You're audible, sir. Please go ahead.
Yeah. Go back to the slide. Okay. Go back to the previous slide. You can see here. Go back to the slide. Go back. First slide. Not the next slide. Next slide. Next slide. Next. 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 No, previous there was an animation. Next. Previous. Yeah. Previous to this. Previous slide. Previous. The next slide. Next. That animation is there now, please. Hello.
Yes.
Yeah,
Sir.
okay. You stop there. Okay. So anyhow, this animation you are not able to track. See what we are doing. One of the thing optical detector is there, optical source is there, and in between some blood sample is there. Blood sample. Okay. So first of all, actually you have given the final this one PowerPoint, but before to that one there were animation of this one only. But what's happening here is, in fact, already we have got one curve for normal blood that is in green color. But if you look, yeah, this is you have gone to fluoride contamination. Let it be here only. I mean, Vaibhav?
Yes,
Hello?
sir.
Yeah, let this be there only. Animation is not working from your system. You can see, first of all, we are having one water, and from optical source is there, optical detector is there. When pure water, we are getting some wavelength. You can see in the blue light, what is in the bottom, you can see the blue spectrum. So next, go to the next. No, there only be there. There only be there. There only. So, and also we pass the light through a contaminated water. You will see you can see the change in the wavelength shift, and it is becoming red. Okay, it is not red actually. For the purpose of understanding you, I am doing this one. Okay, next. Go next.
Yes.
Yeah, now I already given the photonic crystal. Next. Introduction. Okay, I have already given few introduction about it. There are two. Go to introduction. Yeah. There are two types of photonic crystals. One is, of course, one is rods in certain substance and holes also there. There are two different types of periodic variation of. Because of this, we are going to get periodic variation of diffractive index. Next. See, here you can see 1D. 1D means there is a change in refractive index in only one direction. You can see that one. But in 2D photonic crystal, there is a change in refractive index periodically in 2-dimensional. In three-dimensional, you can see in all the 3 dimension X, Y, and Z coordinate system, there will be a variation of refractive index. Next, okay. So 1-dimensional, 2-dimensional, and 3-dimensional. Next. Yeah, this is what the structure. So there are actually you can see the rods in air. That is one of the structure which we are seeing, and holes in some material. So that I am going to discuss. So from this one we can measure temperature, pressure, or anything like infection. Everything we can measure using these kind of sensors. Next, I'll show the few application of it. You can see now. Earlier, whatever I have shown, there are no defects at all. Now you can see there is red line is there now. If I remove the red color rods, the whole line, it will become line defect. And if you remove only one rod, that is yellow, then we have a point defect. You can clearly see in this one. That means if the total line is removed, it is rods in air. One line is removed, it is a line defect. If one rod is removed, it is point defect. Next. So this is a point defect you can see. Next. Next slide. Yeah, you can see here. No, previous. 2 slides. Point defect. Previous. Just yeah. Here. Yeah, be there only. This is a slide which. So now you can see there is no defect. You can see in the left that is periodic variation of refracting in the left one. In the right one, we have shown photonic band gap. If you pass the light through this periodic structure, you can see there is a pass band on lower wavelength and higher wavelength, and in the mid band, that is photonic band gap, you are not allowing. This is not allowing any wavelength to pass through this particular stop band gap. Next. The same thing, the previous one, the same thing. So what I have, no, just go to just previous slide. Yeah, you can see here the red line which I have shown, only one rod is removed. Only one rod is removed. You can see in the spectrum that only one wavelength is being passed in the pass band. You can see remarkable, just one spike. So that is where we are exploring this point defect or line defect to find out many things. Okay, next. Yeah, this is a line defect. Next. Yeah, now what is this PCRR? That is photonic crystal ring resonator. We can construct the same photonic crystal ring resonator for this ring resonator on photonic crystal. It has got a upper bus and a lower bus. In between that one, there is a ring resonator. So if you pass the light through port 1, if it is resonant, it can come out of port 3. It is completely. That means if you give the light input to the port 1, if it is 100% resonating, you will get the output at port number 3. So it is completely what I am telling. It is a micro ring resonator. So the same structure we have developed using photonic crystal. You can see now here. So in the photonic crystal, you can see you are giving the, just be there on this slide for certain time, Vaibhav. Then I will tell you to change the slide. Okay.
Sure.
Please, please look into this wave. This is the structure. It is a photonic crystal ring resonator. It has got only one bus on top of one circle below. That circle is ring. So you can see that one. Both, it is a line defect. First of all, upper one is line defect, and the ring is also line defect because we have removed the rod in the form of circle. That's the reason we call it as ring resonator. Okay. So input port is A and output port is B. So there are rods. How in this figure only I am going to explain many things. You first of all, what I tell you is you fill this with, for example, I'll be giving you 2 examples. For example, we'll take. I have already given in the previous slides that was not changing. I have done some very good animated slide. Unfortunately, it was not changing. So now give the input. You fill this with pure water and pass the laser beam through input port light. You are going to get output at port B. So you will get one wavelength. So that wavelength may be for pure water. Next, you fill this up with the contaminated water, maybe different kind of fluoride contents. Then you are going to see a different wavelength. There will be a wavelength shift from pure water to contaminated water. So depending upon the shift in the wavelength, we are going to tell what type of content. So it may be different kind of fluoride content is contaminated in the water. Or if you want to say, if you want to think about urine sample or blood sample, if someone is infected, first pass the analyte. Analyte means good blood through this waveguide, and you are going to get one particular wavelength. After that, if someone is infected with any disease like virus or bacteria, of course we have done for COVID-19 also. That also in the coming slides you are going to see that one. So then, when depending upon the nature of the infection, you are going to get different wavelengths. There will be a wavelength shift. Each bacteria or virus will have different refractive indices. Because of refractive indices, we are going to have change in the wavelength. That is, change means shift in the wavelength. So that is a signature. For example, we have done for E. coli, Bacillus series, COVID-19. Then in the coming slides, I am going to show that one. Next. Next, Vaibhav. So once again, what is the advantage of MOEMs? MOEMs are thermally, they are stable alignment. Most important thing is thermal stability, faster response, and comparative. It is compatible with fiber optic cable. That is most important thing. That means you can give the input to the fiber optic cable light, and you can get the output to the fiber optic. So there are different applications. Next. So I don't want to go to the history. Next. Okay. So now previous. Yeah, here we can develop directional by using photonic band gap. We can develop directional couplers, Mass-Zander interferometers, Bragg gratings, and micro ring resonators. We have worked on Bragg gratings. We have worked on micro ring resonators. We have worked on directional couplers. Okay, next. Yeah. Now design and simulation. This is one of the thing which we have done in our lab. Crystal-based ring resonator for temperature measurement. Okay, next. We just go through it. We'll see directly next. Yeah, stop here, stop. Before this slide. One slide before this one. No, before one slide before. Yeah. So what next? Yeah, stop here only. So we require what is known as finite difference time domain method for calculating, for measuring anything in photonic crystals. So we are really dependent on FDTD method to simulate photonic crystal structure, and perfect match layer is placed as absorbing boundary for the condition. The technique is extremely versatile. Okay, next. Next. So this is the thing. So hello. Previous. Yeah, you can see the lattice structure. You can see EX, EY, EZ, HX, HY, HZ. There are different components of electric and magnetic field in X, Y, and Z coordinate system. Next. Next. Previous. So I don't want previous. Next. Just next. Yeah, stop here. So the time varying electromagnetic fields obey definitely Maxwell's equation. Then we need to find out the solution of Maxwell's equation. That is possible with our FDTD method. You can see there are basic 4 equations of Maxwell's equation: del dot H, R, and the function of R and T, and del cross E, del cross H, del dot E. But here you can see rho and epsilon. See here, epsilon is permittivity, mu is permeability, sigma is conductivity. All are variable with respect to R. That is a challenging thing here. The next. So these are all the coupled equations. We don't want to move into the mathematics. So earlier we were using MEEP or freely downloadable software which is available now also MEEP. It was done by MIT Electromagnetic Equation, done by MIT Lab USA. but we have in our lab, we have set up our own lab. In that one, earlier we were using NEEP. Now we started using what is that numerical software. Okay, numericals. Next. Of course, it is a paid one. So next, go to the next. Go to the next one. Next. So let me not focus on temperature sensor. So I'll go to the next application. The next. Yeah, now. So this is most important. Previous also that was a application of measuring temperature. Now we are measuring fluoride contents in the water using photonic based biosensor. Next. Previous. Next. Yeah, stop here. See, in our day-to-day life, everybody will dig borewell to get water. But unfortunately, some of the borewells will be contaminated with contaminants like calcium fluoride. So because of calcium fluoride, dental fluorosis will occur. Because of cesium fluoride, nausea, vomiting or diarrhea and bleeding around coma or even to death. Then potassium fluoride, different things, depression, muscle weakness, heart rhythm disorder and confusion. Like that, strontium fluoride will have some different effect. Lithium fluoride will have different side effect. What we can do here, we can clearly tell what type of water is contaminated with which type of fluoride content. So calcium fluoride will have its own wavelength. Cesium fluoride will be having different wavelength. Because of a change in the wavelength, we are going to get change in the what is that wavelength shift. Okay, next. So next. So this also done by MEEP. Okay, MEEP and MATLAB. For plotting, we are using MATLAB. Like, just go next. Yeah, stop here. Previous. Just one slide previous. Yeah. So here you can see the power. Hello. Next. Be there in the slide only. MEEP algorithm. MEEP is a time domain tool, and MEEP is simulation package for computation of transmission reflection spectra. You can see the power is equal to what is that integration of E cross H d square x. Okay, next. Okay, next. So these are all the simulation results which I am going to show you. Next. There is one animated slide. Next. Yeah, animated slide. It's not running. Previous. You can see previous. Next. Yeah, stop here. Just previous. Just one slide previous. Yeah, stop here only. So you can see light is entering from the left side of this ring resonator, and it is going through the bus, and a portion of the light is being coupled with the ring resonator. Next. So you can see the transmission spectra of a pure water. You can see only one peak you can associate it with this one for pure water. That is the signature of the pure water. Next. So calcium fluoride, you can see the maximum frequency will be shifted from the pure water. Cesium also, you can see the peak is occurring in different place. That is the signature of cesium fluoride. Next. You can see lithium fluoride and also potassium fluoride. Next. You can see for pure water, the peak frequency is at 0.2955, but for calcium, it is 0.2919. If the water is contaminated with calcium, you are going to get shift in frequency of 0.0036. Like that, supposing say another potassium fluoride, then the peak frequency is 0.2727. It is the potassium fluoride signature, the shift in the frequency is 0.0228. So because of the shift in the frequency, next we will get the shift in the wavelength also, because wavelength and frequency are once again related. Next. Yeah, next. Next. Yeah, I can see previous, just previous. Yeah, here stop here only. Transmission spectrum for pure water of wavelength shift. You can see for this particular case, for a pure water, you are going to get one wavelength. Next. You can see calcium fluoride and cesium fluoride. You are going to get different wavelengths. For calcium fluoride, you are going to get certain wavelength. For cesium fluoride, you are going to get certain wavelength. They are signatures. Next. Lithium fluoride also like that. Potassium fluoride also like that. So let us see the table. Calcium fluoride. You can see for pure water, the wavelength is 3.384. So that is the signature of the pure water wavelength. Calcium fluoride, if it is contaminated with calcium fluoride, the wavelength shift is 3.426 and the shift in the wavelength is 0.042. Once again, I am telling you the calcium fluoride, the signature is 3.426. Cesium fluoride, it is 3.66 and shift in the wavelength is 0.276. So depending upon the shift in the wavelength, we are going to tell which type of fluoride content is there in the water. Okay. Next. Next, Vaibhav. Next. Next. So this is a total spectra, including everything: calcium fluoride, cesium fluoride, everything. Okay. Zoom version need not be there. Next. Okay. Okay. Next. 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 Be there in the conclusion only. So we have developed this kind of thing very nicely in our lab, and these two previous sensors, the temperature and fluoride sensors, they have won international in the best paper award for these two work from our student. One is Malika and another is Girijamba. Okay, so these results they have done very well, and it has been published in very good journals like IEEE and elsewhere also. Next. So these are the publication out of this work. So next. Yeah, once again, this is the third one which we have done in our lab: design and modeling of photonic crystal nanocavity based pressure sensor. You can see in the top figure A. In the figure A, this is a photonic crystal line defect waveguide. Top is silicon layer, and you can see the outside, and you can see photonic crystal line defect waveguide. You can see there in the A figure A. But you can see in the right figure C, the fabrication details of it is silicon. The bottommost layer is 450 micrometer. Middle one silicon dioxide is 3 micrometer, and on top of the layer silicon is 220 nanometer. So you can go to the figure B. In the figure B, you can see applied pressure. You can see in the A figure no application of pressure, but in figure B, applied, because of the applied pressure, there will be deformity because of pressure. When there is a deformity in the structure, you will get refractive index change in the refractive index. Because of change in the refractive index, you are going to see what is known as change in wavelength. So for each value of pressure applied, you are going to get different wavelengths. Okay, next. So these are all the things which we have taken. A is the radius of the hole, it is 1 micrometer. R is equal to 0.199 micrometer. Height of the stab is 220. The pressure can be applied, can be calculated using P is equal to A omega rho C, where P is acoustic pressure, A is displacement in amplitude, omega is equal to 2 pi RF, so sigma is specific density, C is speed of the light. Okay, the pressure is proportional to the displacement. Next. So this is what actually we got simulation from nanocavity pressure sensor, the thing which I am dealing now. Next. So this is a transmission characteristic spectra. Next. The summary of the work. The sensor previous. The sensor is constructed with two-dimensional photonic crystal waveguide, which is coupled with nanocavity sensor. Okay. The sensor can be used in application requiring high accurate sensing results. The frequency can be mapped by shift in the displacement by using the pressure formula. Okay. So this is also one of the another type of sensor we have developed in our lab simulation. Photonic crystal based mechanical sensor on silicon on insulator platform. Okay, next. So you can see here in the first figure, you can see figure 7. In the first figure, you see this is a ring resonator, hexagonal ring resonator. Second one is the cross sectional view, and third one you can see how you can see the structure. Okay, once again, structure cross section is air by 220 nanometer thick silicon air with refractive index 3.46 and 1 respective. Lattice constant is 420 nanometer. Air hole diameter radius is 120 nanometer. Slab thickness is 220 nanometer. The filling ratio is 0.3. Assure sufficient amount of photonic band gap in TE mode operation. Okay, next. So these are all the different value we are going to get transmission spectra. See the variation in the wavelength clearly. Okay, next. Hello. Vaibhav? Previous. Yeah, be there here for one. Previous. Next. The graph. Next. No, next. Please show the graph. Next. Be previous. Just previous. Yeah, be here only. You can see. Just previous. Yeah, be there. Here only. You can see applied pressure is 4 gigapascal, 3 gigapascal, 2 gigapascal, 5 gigapascal, 1 gigapascal, 0 gigapascal. So depending upon the applied pressure, you are going to get different shift in wavelength because there will be change in refractive index. Next. So the totally what we have seen in this one, a shift in the wavelength or ratio of micro displacements in the proposed sensor up to a quality factor of 1495 and high sensitivity factor of 1200 RIU. What in this one, which I would like to stress you is, if you are using a resonator to get high sensitivity, you should have high Q. Q means quality factor. Okay, next. So design and analysis of photonic crystal based MZI based pressure sensor. Next. So this is another I told you, we have developed different kind of sensors. You can see here Mach-Zehnder interferometer. Figure 12. Figure previous. Be there only. Previous. Next, be there only. Don't change. Be there only. Okay. Just one slide previous to this one. Mach-Zehnder structure. Figure 12. Be there in figure 12 only. Okay. Okay. It is a Mach-Zehnder interferometer. Okay. Be there here only. You can see there are two. There are two arms. One is upper arm and another is lower arm. So what we are doing is here is, by using the Mach-Zehnder principle, we can see left is blue color and right is some gray color. Okay. So what we are doing is, once again, we have taken the same thickness material, silicon 450 micrometer, silicon dioxide 3 micrometer, and silicon 220 nanometer. So what we are doing is, and also the ratio, the refractive index is 3.46 and 1. Okay. Lattice constant to 420 nanometers. Radius is 135 nanometers. Thickness is 220 nanometers. You can see this structure clearly. The left portion is blue. And when we are applying pressure on this diaphragm, this Mach-Zehnder diaphragm, definitely without applying the pressure, you are going to get certain wavelengths. And after application of the pressure, we are going to get certain wavelengths. The gray area of this one is it is the normal arm, So that is the reference arm. The left blue is there now. That is the sensing arm. Okay. Next. We got reasonably good results for this one. And in this one, you cannot be, we have gone for stress analysis. You can see the stress analysis. Next. These are all the graphs of this we have done using numericals. Next. For displacement analysis. Next. Result analysis. Then you can see the transmission characteristic. Previous. So this is the most important thing. You can see here for each value previous. Yeah, be there only figure 18. Figure 18. You can see first one is 0 megapascal. It is coming at around 1.56 micrometer. Okay, wavelength micrometer. You can see in the right side different application of different pressure. There will be a shift in there will be change in refractive index. Because of the change in refractive index, you are going to get change in the what is that one wavelength. So for example, last one you can see for 6 megapixel megapascal, you are going to have 1.564 micrometer, and previous to that one is 5.4 megapascal. So depending upon the applied pressure, you are going to get different value of refractive index. Because of change in refractive index, you are going to get different wavelengths. Next. So these are the result analysis. You can see quality factor is 7047. It's a good quality factor because Q should be very high for getting good what you call sensitivity. For 0, it is Q factor is 7047. Wavelength is 1550.37 nanometer. You can see if you apply 0.6 megapascal, the stress is 0.1987, but you will have change in the wavelength is 1551.51 nanometer, and you can see there is a change in wavelength from when compared to 3.46. For 0, it is 3.46 refractive index. The wavelength is 1550.37. For 0.5 megapixel, the refractive is changed from 3.46 to 3.46307. Wavelength is changed to 1551.51 nanometer. For example, go to 3 megapixel, you can megapascal, 3.47535 is the change in the refractive index. Because of the change in the refractive index, you will get change the shift in the wavelength. You can see 1556.84 micrometer. Like that, you can calculate. Next. So this is a summary which I'd like to tell you. The quality factor of 7000 we can able to achieve. This ring resonator we can go for 30,000 also. So we need to do some more exercise into it. We can improve on the quality factor. Next. So this is another one. Resonator for detection of glucose concentration in urine. Next. Micro ring resonator. You can see here clearly. For normal sugar, you are going to get somewhere around, you can see the figure that is magenta color or what you call. But if there is some 0.625 gram per deciliter is contained, then you are going to have shift in the wavelength. Why shift in the wavelength? For different value of glucose level in the urine, there will be different value of refractive index. Because of different refractive index, there will be change in wavelength. The last one you can see 15, the black one. So by the frequency shift or wavelength shift, we can definitely tell what percentage of quantity of glucose is there in the urine sample. Next. 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 So urea, okay, can go to the next one. Pressure, another pressure sensor structure. Next. Pressure sensor structure. Next. Next. Yeah, we have done another thing. Bacillus series and COVID-19 detection using photonic crystal biosensor. The same structure can be used. Next. So you know that coronavirus is large, roughly a spherical particle with surface projections. The diameter is 125 nanometers. The envelope is 80. The diameter of the envelope is 85 nanometers, and spikes is 20 nanometer. You know that is a protein spike. That is the one which connects or which adhere to the lining of the lung tissues. Next. So this is a COVID-19 virus structure. Next. The next. Bacillus cereus. Next. So next. You can see previous. Okay. Next. You can see the, okay. Next. Next. Okay. Next. So next. Next. Oh. Next. Okay. I think previous. See different previous. No, the ring structures. Go to the ring structures. Previous. No, next, not previous. Next. Stop here. You can see it is a ring resonator structure. This is how it works. Next one. Yeah, I can see. Figure 7, split ring resonator. You can see a small portion of the ring is split. Figure 8 is a double ring resonator, and this is asymmetric. So 2 rings are there in between 2 buses, but one previous ring resonator. Yeah, in one of this one. Next. Figure 7, 8. Yeah, 9. Figure 7, 8, 10. Hello. You can see here. Can you see here? Figure previous. Yeah, be there in this one only for 1 minute. Split ring resonator. Second one is figure 8 is 2 rings are there. This is asymmetric ring structure. And figure 9 is double ring and figure 9 is symmetric one. Okay. Figure 8 is asymmetric rings. Figure 9 is symmetric ring. Okay. Next. Applications. You know that one. I already told. Next. Yeah, you can see different structures how we have made. You can see from the top view of this one, rods in air structure, and this is DFT amplitude simulation diagram. Okay, good. Next. So it is a double hexagonal ring resonator. Next, not previous. Next. Result analysis. Next. Go to the, I think, last slide now. Yeah, last slide. Next one. Oh, okay, be there on this slide. So stop here. Go to the last slide. Thanks slide. Yeah, thank you very much. Once again, I would like to conclude my talk. So in this totally, I have taken you to the various type of photonic bandgap semiconductor photonic bandgap crystal sensors. All the things we have done in our lab only. Right now, under me, 35 students, UG, PG, PhD are working in our lab, in photonics lab. And we are getting reasonably good results. But unfortunately, we are not able to fabricate. So fabrication needs to be done in IISc. And to be precise, if you want this thing to be what you call reality, we need what is that one is on a fabrication facility, very good fabrication facility. It can be done only in abroad. I'm telling you, this is the whole concept is lab on chip. What do you mean by lab on chip? We need not have to go to the pathological lab now. So on a small chip, if you pour water, if you pour urine, if you pour what is that one blood, you can definitely measure what type of water is contaminated, what type of bacteria is invaded into the blood, what type of bacteria or virus invaded into the blood and urine. You can clearly tell. So this is what the application of biological sensors. And another application is pressure sensor. Pressure sensor also we have done it. So once again, there are many medical applications of pressure sensor. This can be used in what is called measuring pulse, blood pressure, intracranial pressure, so etc. And also it can be used to measure normal day-to-day life pressure. And also, apart from medical applications, we have one more thing, structural monitoring. You know that civil structures, bridges and all those things, they should be monitored. How much pressure it is withstanding, what is the vibration it can withstand. For all those things, we need what is known as pressure sensor, and internet is a vibrational sensor. So with all that one, I think, now I think Dr. Sara is sharing my screen. Am I right? Hello?
Hello, yes, sir.
Yeah, I think now I am done with my, presentation. Anybody is having doubt, you are most welcome. Sorry for the inconvenience. There are a lot of things happened in today's talk because of technical stack. So I am not able to concentrate much on my topic, but anyhow, I could able to deliver whatever I wanted to do it. I have delivered. Any questions from the audience? I'm ready to take up.
Any questions from the audience?
And also one more thing I would like to tell you, those who want to do their projects like BE and ME, and also even PhD, our lab is available. We have got very good lab in our department. We charge nominal charges for any research for the students. And those who are interested may kindly approach me directly. I have, I think you know my email ID. It is given in the brochure. And also I think you can directly contact me over email pcs@mcehasan.ac.in. Okay, madam. And I will handing over to you.
Yeah. Thank you, sir. Thank you, sir, for such an informative presentation. And you have shown light on various aspects of the photonic sensor. Your talk on the photonic crystal ring resonator temperature sensor and the use of ring resonators for various applications was also very interesting. So all the participants for this conference have been greatly benefited. Thank you very much, sir, for sparing your precious time, sir.
Okay, thank you. Sorry for the technical stack.
No problem, sir.
Thank you very much, sir. No
Thank
problem.
you very much, sir.
Thank you, doctor.
I now request Mrs. Anna Marin George to introduce the next keynote speaker. Anna.
Thank you, Rajeshri ma'am. Our next keynote lecture is on EDA challenges in semiconductor industry, semiconductor chip design by Mr. Santosh Kumar Adinarayan from Maxim Integrated India Private Limited. So let me introduce the invited speaker, Mr. Santosh Kumar Adinarayan from Maxim Integrated India Private Limited. So Mr. Santosh Kumar Adinarayan did his BE from SIT and MS in microelectronics from BITS Pilani. Currently, he is pursuing his PhD at Jain University. He also has obtained various professional certifications from Program Management Institute and Indian School of Business. Currently, he is working as a design center manager at IC Design at Maxim Integrated. He started his career at Raman Research Institute, Bangalore in 1992, where he worked on design development and commissioning of data acquisition systems, signal processing systems for radio telescope, and VHDL bar Verilog implementation on FPGA bar CPLDs. He also has a rich semiconductor industry experience with IBM Microelectronics, Texas Instruments, Infineon, and Rambus. He has worked in all phases of VLSI design, and He has created and managed teams in ASICS and EDA domains. He has a passion for improving industry-university relationships in the areas of VLSI and embedded technologies. So with these words, I request Mr. Santosh Kumar Adinarayan to take over the session.
So thanks for the introduction. Can you all hear me?
Yes, sir.
Okay, yeah, thank you. So let me just start sharing my screen. Give me a minute. Okay. So I think you are able to see my screen, right? Give me a minute.
Yes, sir. We are able to see this.
Yeah, one minute. Okay, sure. Okay, so yeah, thanks for the introduction, and thanks to Dr. Vaibhav for inviting me for this particular conference. And so basically, I'm going to talk about the EDA challenges in semiconductor design. And as I was introduced, I'm currently working with Maxim Integrated, which is a semiconductor IC design company. Okay, so just a quick introduction about what we do in Maxim Integrated. So we are basically a mixed signal analog and digital semiconductor company, and we actually cater for many different markets in terms of healthcare or in terms of wearables, where we actually make chips for measuring the heart rates and all the Fitbits and so on. You have this our chips there, or we actually make semiconductors for data centers, communications, and so on. So this is a very broad kind of company, and also we make specifically in terms of power, in terms of power management designs. Okay. So basically, my talk is going to actually talk about the semiconductor design complexities and what we can actually do about it, right? And all of you have known about this Moore's law, where it actually says the number of transistors per square inch on an IC, it doubles once in every 2 years, right? And so this is the historical chart, how the number of transistors are increasing and so on. And all of you definitely would have studied in your theories in terms of how we achieve it. We basically achieve it by the scaling of CMOS transistors. And in this particular case, I'm showing a constant field scaling, wherein you try to reduce the dimensions like the length, width, and T oxide thickness and so on by 1 over A. And you have the doping also. You keep the doping constant, and the voltages also decreases by 1 by A. And this is how you actually try to shrink the design, and this way you can actually make the performance of the design also go up. So the delay actually decreases, and the power dissipation also actually decreases. And so basically what you are doing is, when you shrink the design, your delay reduces, so your area reduces as well as your performance increases, right? And that is why we are able to go for like starting from few megahertz kind of designs. Now we are actually talking about gigahertz kind of designs, right? But this also brings about a lot of challenges, how we can do. And this is mainly this constant field scaling can actually be done for digital circuits in general. Okay. So if I go further, in terms of Moore's law, of course we have seen from 180 nanometer to 130 nanometer, 90 nanometer. So basically it used to follow the same trend in the previous years, till about 2012 or 2015 kind of time frame, right? But now what is happening is, like, it is actually taking a little bit more time to get to this 2x kind of improvement. That is mainly because there are a lot more challenges in terms of, when we go to deeper submicron nodes or even almost like, nano kind of technology. And so basically, as we go to 14 nanometers or 10 nanometers or 7 nanometers, which is already under production, but we can see the Moore's law is actually getting, little bit slowed down. And this slowdown is mainly happening because of several technological challenges that is happening. And of course, as we go to 7 nanometer or 3 nanometer is also under talk. But there can be an end for Moore's law, right? But that does not actually stop us from innovation, and we have to actually continue to do something what is called as more than Moore. Okay, so basically this is the more than Moore concept, which is actually shown here. So in the y-axis you can see that the technology scaling, which can happen from 130 nanometer all the way to 65, 45, and 22, and even beyond that, 10 nanometers and so on. This can actually go on in terms of in terms of the digital circuits. So basically, where it will be mainly for information processing or the digital content on a system on a chip. I mean, it can definitely take this route, but then there are limitations, right? But whereas in terms of more than Moore classification, what we want to do is we want to actually also try to optimize the analog circuitry or the passives or the sensors and actuators and the biochips and so on. And so this is the main concept that is actually coming up now, and especially all the mixed signal design companies like Maxim Integrated are really putting more and more focus on how we can enable this combining the analog as well as the digital kind of information, right? And to do this, definitely, there is a major research and advancements that are needed in almost all facets. The materials, it requires a new kind of advancements, that we have seen. There are several new materials which are actually coming up, or in terms of modeling, how we model the analog and digital, and especially the analog functionalities in terms of the EDA. So this is the portion that I'm going to focus today, which is nothing but the electronic design automation. And so this actually enables all the different tools and methodologies and so on for designing a chip. And of course, there are many other things connected with packaging, connected with system design and so on. Right? So this is the ultimate goal, is to go in this trend of minimization, as well as putting more and more complexity into the design or functionalities into the design, and give rise to the higher value systems. Right. And as I talked about, the critical EDA is a very critical portion to address what we are talking about in terms of increasing the complexity of the systems and so on, right? So basically, this slide shows the number of transistors in a different perspective. The number of transistors and so on, they actually were growing around 58% compounded complexity growth. This is of course a dated slide, but this actually shows the importance of EDA. And so when this kind of complexity grows, we need to have some kind of CAD tools, as well as methodologies, how we can do hierarchical designs and so on, to address this kind of complexity. Otherwise, we would not actually try to meet the design productivity that is actually needed. And this design productivity is basically provided by the EDA tools, right? So and when I go to a classical EDA or VLSI design, so basically we go through different domains. Basically we try to specify the design in terms of its behavioral domain, wherein we would call it as a system, and then this system can actually have some processors, and then these systems and these processors can do a particular algorithm, and then this can actually be implemented by using the different ALUs or RAMs and so on in the processors. then there can be a lot of logic operations and so on, and which can be implemented by gates and flip-flops, and then we finally go to the transistor level designs and so on. So this is basically coming from a top-down kind of thing. And similarly, even in the physical domain, we actually go from physical partitions to floor plan to module placement, and finally we'll reach the transistor layout. So the end goal is to do a kind of top-down structural design. That is the one which is actually used in most of VLSI design nowadays. Right? And this is another snapshot of how we do the design flow. As I mentioned, like we'll have the system specifications, then we come out with the architectural design, and then we actually do the functional design and logic design of the criteria that we are looking for. We do the circuit design, then we actually go into the physical design. And in this talk, I'm also going to concentrate more on the physical design aspect of EDA. And then we go to physical verification, the fabrication, the packaging, and then finally the chip comes out of the foundries. Right? So I will actually be mainly concentrating on the EDA that is actually required for the physical design portion more in this particular talk. But of course, EDA is actually required for all these aspects, in terms of architectural design or in terms of circuit design or fabrications, and in each and every step, you need to have the EDA tools. Okay. Going further, I will quickly introduce you to what a chip partitioning is. So basically, partitioning is nothing but dividing and conquering a very huge problem. And as I have said, the complexity of the designs are actually growing day by day, and we need to have some mechanism by which we can divide and conquer the design. And so basically, this is actually showing a pictorial version of what we do in terms of divide and conquer. Right? So suppose if you have a circuit like this, which has 8 different gates, and if you actually take a cut A, or so basically we would actually suppose if you actually take all the left side things and then put it as block A, and right side gates and put it as block B, there are 4 connections which are happening between the blocks, right? And in terms of partitioning, one of the main criteria is how we can minimize the number of the connections which are going between the blocks. And so this is one of the main criteria whenever we do any kind of partition. So we will not actually just do it like a vertical cut, but we will actually do it like like another cut, which is called like cut B here, wherein we rearrange the gates in such a way that the number of external connections are much minimum. Right. So for doing this, we actually do several of the graph-based techniques and so on in EDA to look at how many connections are happening between the blocks. And if we do not do this, I'm just showing one example of a huge design which can have several things like it can have a HDTV, or it can have some crypto block, or it can have some DRAM interfaces, audio interfaces, video interfaces, and so on. And if you want to design this kind of chip, there is no way that you can actually design the whole chip as a flat module. So you need to do this kind of divide and conquer, and this divide and conquer can be done by associating the like functionality blocks, as well as ensuring that there are not many interconnections which are going from each block to the other block. And it's more like each blocks are like interconnected kind of blocks. So this is just an example of what we do here in terms of partitioning. Okay, and so similarly, even in a mixed signal design, as I mentioned, we are predominantly a mixed signal company. So a mixed signal design can have almost like 75% of the design can have analog, which can have ADCs and DACs and many other analog components. And we can even have 25% digital, right? So when we are actually doing an analog and digital partitioning, again, we have to take proper care that all the digital and analog, the interfaces are quite minimal, and there are no signals which go back and forth between analog and digital, and we need to really take care of the partitioning in a very big manner. Okay, and whenever we do this partitioning, this will also have a huge impact on the verification also. So in terms of the digital, we all know that digital can actually be represented in high-level descriptive languages like Verilog or VHDL or System Verilog and so on. And so here the verification would be much faster because we will have event-driven simulation technologies. So based on the clock edge, we'll know when something is changing and then what will be actually registered and so on, right? But whereas in pure analog, we'll have either SPICE or fast SPICE, or we'll have RF kind of characterizations, and these simulations would actually take much more time because these are not event based, and these are actually going by a step-by-step evaluation of the circuit at each time step, and this would actually take quite a lot of time. And in the middle, we'll have things like analog behavioral modeling, wherein we can have a behavioral model for the analog, in which can actually be simulated using the digital simulators. So the key point is that the partitioning is really required for both digital designs as well as the analog and mixed signal designs. Okay. And going further, in terms of chip design, we need to do what is called as floor plan. Floor plan is nothing but the activity wherein we are actually saying which blocks of the design would reside where. Okay. And so, for example, if we have, let's say, 3 blocks, A, B, C, and each one of them can actually take different sizes, based on, suppose, their area is fixed, but you can actually make A as either, 1:4, or, you can actually make it as 4:1 kind of.
Sir, you're not audible, sir. Santosh, sir. Sir, I think you're not audible.
Participant. Okay, yeah, thanks. I think somebody had muted me. Can you hear me now?
Yes, sir.
Okay, yeah, thanks. So yeah, I think there was some glitch. Okay, I was talking about floor planning. Why it is very important. So basically, suppose if you have 3 different blocks in your design and each of them can actually take different aspect ratios. Now you will have to do a kind of iterations, in terms of which aspect ratio would be best suited for your design, right? So what you would actually do is you would actually take the best possible aspect ratio that would end up giving you the overall lesser area or overall minimum area, having all the 3 blocks, right? So this is just a pictorial representation, how we have taken 2 by 2 for A design, or for B and C design, we have taken the other 2 aspect ratios, right? And then this actually gives you the lowest minimum area, the total area, right? So, and then that is about the chip planning, and even here in chip planning and so on, we have several EDA algorithms that will work. And in terms of placement, there are. This is again a dated slide. We do not do any kind of linear placement nowadays. So whatever the netlist that we have, it can be placed, and of course, it can also be routed later on. So it can be placed either in linear placement, which is like only in one direction, like X, or it can be placed in 2 dimensions. And the idea again here is to see that we are actually placing each of these components very close to each other, and also the wire length between the components, which is actually the nets which are going from one block to another block, or one gate to another block. It's not too big, right? So those are the main optimization criteria in terms of placement. So basically, we try to make sure that the total wire length is small, the number of cuts is small. When I say cut, I mean so basically you take any particular vertical cut here, you should not have too many wires going between them, right? Or the wire congestion is small. Wire congestion is nothing but how many wires can actually pass through a unit area. And then you cannot have too much of signal delay, and these are the optimization objectives. And for each one of them, like we'll have different kind of algorithms running in our EDA tools, which can actually make it happen. And in terms of the complexities, as I mentioned, there is high complexity. There will be millions of objects in one design. So we need to have a scalable solution which can actually place all the different cells in the design properly. And then whenever we place the cells, we have to also take care of the placement constraints, like what kind of blockages are there, what kind of routability densities, the timing and region, and so on. And so basically, this is more like it is a multi-dimensional problem, right? And then we need to also look at mixed size placements. There can be few macros or memories and so on, which will be of different sizes, and they have to be also placed, and you have to also place all the other gates and so on. So there can be thousands of big macros and several millions of smaller cells. So we need to take care of heterogeneity, as well as in the coming days, we are also looking at how to integrate 3-dimensional ICs, and how to how we can actually optimize the data paths and the kind of FPGA field programmable arrays and so on. So for all these things, we need to really take care of all these technologies and so on in our placement. Okay. So going further, I would like to talk about, once we do the partitioning, then the chip planning, then the placement, we actually do the clock tree synthesis. And so clocks are very important in the design, and because this is based on the clocks, we will actually determine when a particular signal is either sampled, or when it is actually held in the memory, or what kind of operations happen and so on. So that is the reason the clock tree synthesis is very, very important factor in our VLSI design, right? So if you see the clock distribution, here I'm showing a pictorial representation. So suppose if this is the clock pin in the design, and this has to eventually reach each and every flop in the design for which it is actually driving, right? So, but the physically, you will not be able to distribute this clock to each and every flop in the design at the same instant of time, and it cannot also have a perfectly regular period. So this is the main problem, and because of this, we get into what is called as a clock skew problem. Or clock skew is nothing but it's a spatial clock variation. So basically, in the design, on the die, you may have one flop which is very close by, and the other flop which may be very far. So the arrival time for that particular, for the clock which is for the flop which is nearby, maybe the clock would actually arrive a little bit early, and for the flop which is slightly which is slightly farther away, the clock might actually come a little late, and this gives rise to the clock skew. And this skew has to be avoided as much as possible, and then we do a lot of optimizations in the design. reduce this clock skew, because this also gives rise to the timing problem. Suppose, if one flop is launching a data which is getting captured in B, but the capturing clock itself in this case, it is coming earlier. So which means, there will be timing violations both in terms of setup and hold. So we need to catch them. Or in terms of, there can be some kind of temporal clock variation, which is nothing but clock period can actually jitter, or it's called clock jitter. The period in A is not equal to the period B. So which means, if you are, let's say, sending some, 100 megahertz or whatever frequency, sometimes, it can become like, 99.99, and then the other time it can be 100, or the other time it can be 100.01 or whatever. So you can have that kind of small jitter, and this jitter also plays a big part in terms of timing closures. So you need to also avoid this, right? And so basically, to avoid these things, we try to distribute the clock with very less skew. So in the sense, like, we try to make recursive patterns, wherein all the leaf cells would actually, from the center of the clock, it'll actually reach everything, all the leaf cells with the same delay, right? And so this equal delay is very important. Or, we can actually make it with the RC tree, wherein we can have different routing length to ensure the same delay is actually is achieved at each of the clocking points for each of the flops, right? So, and to do this, there are different kinds of algorithms that we follow, right? So in terms of, we can have what is called as MMM, or means and medians. So basically, given all the leaf cells in the design, or the flops in the design, we identify the center of gravity. So we first try to feed the clock to this particular place, and from there, we try how we can actually, partition the design. So basically, here, we are trying to divide the design by means of center of gravity. So let's say, eight flops would get on the left side, 8 flops would get on the right side, and so on, right? And then, we find the center of gravity for each one of those clusters, and then, we try to connect them. And then similarly, we again break it down into 4, 4, and then we again find the center of gravity there, and then again we divide it by 2, 2, and we find the center of gravity. So this way, this means and medians, this approach would actually give us the final intention of that, we will have all clocks will be reaching all the flops at the same time, so that, we'll have minimum skew, right? So similarly, there is also kind of, recursive geometric matching, wherein, we try to have different pairs of these different flops, and for each of the pairs, we try to have, the min cost or geometric matching. So basically, we try to see which is the nearest flop that is actually there, and we match them up, and then, we try the center of gravity for each one of them, and from there, we actually, try to put the balance points and connect them, and finally, we try to make the kind of a H tree kind of thing. And this is again used for doing the global, minimizing the global skew, right? So then, once we achieve this, then, most of our timing related issues, that is both the setup time and hold time, that will be balanced, right? But on top of this, we have something called on-chip variations. So by on-chip variations, what it basically means is like, suppose you have the clock, which is actually, launching a data, as you can see in the lower left-hand side corner, which is launching the data, and then it actually goes to the capturing place. So the clock is same in a sense, like, it goes to flop 1 as well as flop 2. So basically what it means is like, the launching path is this, the top, and the capturing path is this, right? And in this launching path as well as the capturing path, you can have different variations in terms of the cells that are actually used here. So So basically, we were actually using something called OCV, that is on-chip variation modeling for this, by which we used to derate the launching path as well as the capturing path by different amounts, and then it was a flat global margin, and we used to take care of this pessimism, right? And then, after 40 or 65 nanometers, we could not continue only with the OCV margin. We need to go for what is called as advanced OCV. So in advanced OCV, what really happens is both the depth of the logic, in this particular thing, you have, one stage, second stage, third stage, and fourth stage. So depth is nothing but you can consider it as a number of stages. And it'll also have unit distance, how far it is. Now based on this, you can have the delay variations in each of these cells happening at different levels. And because of that, you will also have the launching path as well as the capturing path will be calculated, and then you can do a better timing analysis, right? And then for sub 20 nanometer kind of designs, what we need to do is, like, we need to do something called the POCV, or the parametric OCV, or they call it by different names, right? So basically, each of these cells in the design can actually have its Gaussian distribution, and each of them can actually take different values based on which location in the design or on the die they are, and then we can actually apply different uh, different POCV constants for the launching path and capturing path, and then finally do the timing closure, right? So as you can see, as we go for lower and lower nodes, the clock is becoming a very, very major thing to handle. And if you don't take care of the clock, or any of these variations and so on, variations are also becoming much higher. It becomes very difficult, right? So because of this, there is also some kind of research that is happening in terms of how we can do asynchronous designs. So basically, in the top, you can see that asynchronous design, it has a global clock which goes to all the clocks, right? And based on the clock edge, you move the data, or whatever operations that you are doing, from one block to the other block. Or this can be anything. It can be either adders, or it can be some memory elements, or whatever, right? But whereas in asynchronous design, the idea is, like, if we completely eliminate this global clock, and if we can actually do it more like a kind of a handshaking mechanism between two blocks, two processing blocks. So basically, the one processing block would say, okay, I'm done, and then the next processing block would actually pick up the data, and then it'll start the process. Once it actually picks up the data, it would also say acknowledge. So basically, it will work with a kind of the data availability. It's more like the request and acknowledge kind of handshake mechanism. It's basically a sender and receiver kind of path, and this can actually work for several designs. In terms of we can have asynchronous FIFOs developed, or we can have asynchronous DSP kind of architectures. We can have many of the asynchronous designs. The main advantage is that now that we do not have clock, the timing and so on would be much more easier to handle, as well as there will be also the clock, whenever it actually switches, each switching element in the design would also give rise to power consumption. So we can also have lesser power with asynchronous design. So this is still in the research domain, and then several people are actually working on it. In fact, my area of interest is also in the asynchronous design area that I'm working on. Okay, but of course, we do not have commercial EDA tools available for full-fledged asynchronous design, as I have noted down here. But there has been several commercially successful designs by many different companies and so on. Okay, and so this is one thing on the clocks. How the research is moving, right? And then once we complete the clocking of the design, either with the proper synchronized clock or with the asynchronous design, Then we come to the signal routing. So basically what signal routing is, you have a net list which gives all the nets, which says which block is connected to what and so on. And you have the placement, right? And depending on the technology rules information, it has to go ahead and then route the design. So basically you will have the placement, the net list, and also the technology information. And then it will know, okay, in this particular case, let's say N1 is connected between this pin of whatever B3, and then it is connected to D6, and it is connected to C4. So this gets connected, and then the whole thing gets connected based on the technology rules information. So there should not be shorts, there should not be any opens, and all those things. And the main thing is like, we optimize these things with respect to many routing objectives, like minimize the total wire length, maximizing the timing slack, and so on. Right? And so there are different routing models that are available in the industry, like the grid-based router, wherein what is your design. Suppose if it is, let's say, X and Y, it is divided into a series of grids, and these are regular grids, and that the connection has to happen only on this grid, right? And so this was predominantly the format in several previous generations of the technology nodes. But now, we are also going for gridless routers, wherein we do not have this specified predetermined grid, but we can actually, route it anywhere, as well as, we can also have different width of the nets that can actually happen, right? So I'm just showing one example of a routing on a real design. This is basically with the grid-based routing. So basically you have the placement, once you have the placement, all these pins are here, and then you have the wiring tracks. And, first you identify these wiring tracks, and then you go to global routing, wherein you say how many nets are getting connected within a particular unit area. And once you know how many nets are passing and so on, this should not be more than 100%, which is actually shown in the congestion map. So, and then, then once the congestion is under control, you actually do the detailed routing. And here you can see all these connections, which are properly connected on the wire track and so on. Okay. But the main challenges in our in the detailed routing, as well as when we go from technology nodes, is that the wire delay is actually becoming much higher than the gate delay itself. For example, here we are showing this interconnect delay with this blue thing, right? So the interconnect delay itself is actually becoming much higher than the gate delay. Gate delay, as we have seen, because of the scaling, the delay of, let's say your AND gate or NAND gate or whatever gate, that gate actually, that propagation delay itself is reducing, but whereas the interconnect delay is increasing, right? And so not just the interconnect delay, which is mainly due to the length of the interconnect as well as the width of the interconnect and so on. So basically the RLC. And what is also important is the interconnect delay due to crosstalk is also increasing. Crosstalk meaning, suppose if you have two wires which are actually running parallel to each other, you can have some kind of cross coupling capacitance between them. And because of this cross coupling capacitance, you may have delay variations. So whenever we design any of our circuits, we have to take care that the interconnect delay as well as the crosstalk delays are actually properly handled, right? So yeah, in this slide, I'm actually talking about the crosstalk noise and delay problem. So basically, as I said, we have two lines which are going very nearer to each other. You can have one of the lines can be an aggressor, the other one can be a victim. So whenever one is switching, even though the other one should not switch, but you may have a spike there. And if this spike actually exceeds the threshold values of the receiving gate, then you can have a logic error that can actually happen. So for example, in this victim, like you have this high threshold or or high noise or low noise coming into picture, right? So and if this high noise, if it actually goes above a particular limit, it can actually trigger wrong values for this particular gate. Right? This is one of the problems, which is called the crosstalk noise. The other problem is nothing but crosstalk delay. So here what happens is, like, whenever the different aggressor and victim nets, they are switching. So the aggressor net switching can actually have a kind of timing impact on the victim net. So in this particular case, these two nets are actually switching in the opposite direction. And when they are switching in the opposite direction, we can see that the victim net is getting delayed by some amount. And this kind of delay is called crosstalk delay. And this kind of both noise, crosstalk noise, as well as crosstalk delays, they give rise to a lot of functional issues as well as timing issues in the design. And our EDA tools will have to take care of all these phenomena. Right. And next, I move on to the next section, which is more like, now we have completed the placement, we have completed the clock, we have completed the routing, and now when we actually come to the how we actually realize this on the circuit. So we basically use what is called as lithography, and here I'm actually showing you a kind of previously, or kind of old technology, in the sense, like, we have optical lithography here. So wherein you illuminate the mask by means of a light source, and this would be actually projected onto the wafer. And so here you can see that the what is the smallest dimension that we can actually represent on the final wafer. It depends finally on the lambda, that is on the wavelength of the light source that we have, right? And so it actually depends on several other factors also, but it mainly depends on the wavelength of the light source, right? So, and we do have a kind of limitation with optical lithography, that we cannot actually go down to below 0.25 nanometers and so on, or even below 90 nanometers and so on. We could not actually use the optical lithography, and then we had to move to EUV kind of thing, right? So here it actually shows some of the limitations, and basically even when we do this lithography, if we are actually trying to draw a rectangle on the wafer, but the rectangle itself may actually not be represented like a rectangle. I mean, for example, here we are actually wanting to put a T here, but the printed layout, it actually comes out with some kind of rounded edges and so on. Or in this case, like we can see that all the rectangles and so on, they have rounded edges, right? So with the optical lithography at those days, we used to do something called optical proximity correction. So wherein, whenever we need this kind of pattern, for example, we actually add a few more, blocks, or a few more at the edges, we actually, introduce, few more, smaller squares or smaller rectangles. And then, when we expose this, we actually get the required pattern. And these were actually, mainly done with optimal proximity corrections and so on. These were usually used to happen up till about 130 nanometers and so on. And even beyond that, there used to be some kind of aggressive optical proximity correction, which used to happen up till 65 nanometers and so on. But later than that, we cannot still continue with only proximity correction. And then we need to go for what is called as double patterning. So by double patterning, what I mean is, like, we need to consider the whole design as two different colors. Or in fact, now there is also, like, there are also multiple patterning which are actually coming into picture. So basically in this particular thing, I'm showing only double patterning here. So wherein you can see, one of them is blue, the other one is red, or some kind of some tone of red, right? So you basically expose only the blue a mask initially, and then you expose the other mask, and then combining these two, you would also get the exact shapes that you want. And this is basically done for all nodes which are actually less than 22 nanometers and so on, right? And so basically this is how we actually try to take care of the lithography issues and so on. And then, as I mentioned, like you can also see in the older technology nodes, we used to use the sources like light sources with 193 nanometers or 248 nanometers and so on. But still, we were able to get to higher things, by means of optical proximity corrections or by means of double patterning and so on. Now we are actually moving to EUV kind of lithography. So I'm not talking about those things here, right? And so basically, now this actually completes, more like till the manufacturing state. But I wanted to touch upon another major factor in our VLSI design as we go to the next technology nodes and so on. So basically, why do we need to care about power? I mean, because any of our handhelds and so on, that needs to have lower energy consumption, and that needs to give rise to higher battery life. That is one thing. And even for any of our which is always connected kind of thing, either the laptops or any other data center and so on, you will have several computers, right? So there again, we need to ensure that the heat dissipation is low, as well as we need to really do something called like go green kind of methodologies, right? So that is the reason the power is also an important factor in the semiconductor design, right? And so basically, what happens is like in semiconductor design, the total power is classified as static power as well as the dynamic power. And so the static power is nothing but how much static, even when you just keep the keep the cell phone off, even when the cell phone is off, but there will be some kind of static current which is actually going through the circuit, and that actually takes some power, right? And so for doing this, we need to actually, what we try to always do is like, we will try to reduce the voltage, or we use lesser number of transistors, or we also use lower leakage transistors. So the leakage current itself would be lower. So we can actually get to lower static power. Or the other mode is the higher dynamic power. So the dynamic power is mainly dependent on how much of the design is actually switching and at what time it is actually switching. And so if all the design is completely switching all the time, then there will be more power dissipated in the design. So the first thing that we have to do is like we have to decrease the switching activity, whatever that we can add. So there are many techniques that we can do here, in terms of clock gating, or in terms of doing different kind of switching activity corrections. I'll talk about it later. But these are the two main primary things which actually take away both the static power as well as the dynamic power. So in terms of power reduction techniques, there are several ways that we actually use. And this can go all the way from the ASIC front end, that is from the architectural definition phase. We can do, as I was saying, we can do some power gating. So we can switch on some blocks of the design, we can switch off another blocks of the design, or we can have multiple VDD. A few blocks can have higher voltages and few blocks can have lower voltages. So whichever is actually switching more, you can run them at a lower voltage so that your dynamic power will be reduced. Right? Or we can have power modes. You can have sleep mode, or you can have standby mode, or you can have some kind of always on mode kind of thing. You can have different architectural techniques. And generally, the architectural technique, they give the maximum amount of power savings, right? And so then when we go to the once we have decided about the architecture, then we can go for the synthesis and net listing and so on. At this stage, we can do some kind of clock gating or multi-VT, which is nothing but, as we talked about before, we can change the VT of each of the each of the gates, right? And or each of the standard cells, they can be at different voltages, and they would actually give rise to smaller power, right? Or there are also advanced techniques like body biasing, or we can also do things like minimizing the parasitics and load and so on, right? And all these things would also give rise to power savings. And in all these areas, we have a lot of EDA algorithms as well as EDA techniques with which we have to do this. And in the previous generations, what we always used to do is like we used to go in a kind of a streamlined fashion from floor plan placement, optimization, clock tree, and so on. And these used to give a kind of predicted timing. And when I say predicted timing, we used to definitely get what we had designed for, and then we could actually do the simulations, and then we need to predict the timing at each step in the design. After placement, what would be the timing, after optimization, after clock tree, and so on, and then we could do the final timing sign off. But with the growing complexities in the chip, as well as growing complexities in terms of the variations in the design and so on, so this is no longer working for the advanced nodes. So we need to do some kind of machine learning based time prediction and optimization, and several EDA tools have now started doing this. So basically, they just don't learn only on one particular design. They do not just take the timing data and then do the they do not predict the timing. They actually take several designs. They can be families of designs and so on, and then they can actually do a kind of machine learning to look at what kind of effects it can have, and they come up with a machine learning timing model. And using that timing model, we can get a better predicted timing, and in the improved, and there will be improved prediction, and in the final timing would be much more better. So basically, these are the kind of things that are happening as of today in terms of EDA. There is more and more machine learning that is actually that is being researched upon, as well as that is put into the design tools. And also, as chip designers, we need to really collectively think about like how we can learn from the previous designs and how we can make these timing models better, right? And again, this actually talks about not only in terms of timing predictions, but we can also have in all phases in the physical or in the VLSI domain, we can have a machine learning concept applied. And we can get faster conversions by doing proper predictions, as well as we can have faster runtime by having a proper machine learning classifiers by which we can classify the macros and macro cells and so on into different floor planning areas, or the partitioning and so on. Or we can also get better optimizations, and then we can get better QOR. And last but not least, we can also have better schedulers, wherein we can actually run the job in parallel on multiple machines and or multiple servers. And then finally, we can also integrate the full design. So even here, we need to have a lot of machine learning. And here in this particular thing, I'm just showing what are the possibilities in terms of machine learning, application of machine learning in terms of EDA and chip design in general. And as you can see, it can be applied for the full breadth of the VLSI flow. This is only the implementation flow, but also in functional verification, or in terms of layout verification, or in terms of many other power estimation. In all those areas, we could actually apply machine learning. Right? So as I talked about few of those things, definitely, we have a deluge of new design challenges. right from the layout based effects to, like we talked about some DFM like OPC and, double patterning and so on. So we had to do metal filling. We did not talk about each one of them, but we did touch upon few of them, but as you can see, there is a lot more complexity that is going on in the design, and all these things had to be taken care when we actually, finally do the design, and when we finally, before we do the tape out to the foundries, before they can actually, produce the design. So we have to take care of all these different challenges, right? I'm not going to read out each one of them. But the complexity is definitely increasing, and we need to take care of all these things, right? So, and then finally, I would like to conclude by saying that the world is definitely changing. Definitely, there are many more smart things that are coming, and we need to actually, do more collection and sending of the data, or we need to turn those data that we have into intelligent decisions. And so, basically, the final aim is to improve the way we work and live and play or whatever. And this is mainly enabled by the semiconductors, which can actually provide accurate measurements or good communication or efficient energies, and also small form factors, right? And all these things are also enabled by the electronic design automation, which will actually runs completely in the background of all these designs, and we can make it happen. So yeah, that's all from my side. I can take any questions, if any.
Thank you, sir, for your presentation. If the audience have any questions, they can put it in the chat window.
Yes.
The audience have any questions, they can put it in the chat window.
Yeah.
So what are the different power optimization tools available for
yeah,
EDA design?
Yeah, there are different tools available from different EDA vendors. You have EDA vendors like Cadence, Synopsys, and you have several other EDA vendors, and each one of them, they have their own power optimization tools. So each vendor will have their own tools, and we do use different tools as and when needed. And there are tools like Red Hawk, or there are tools called Apache Designs and so on. Or from Cadence, we have tools called Voltus. Or from Synopsys, we have tools like Prime Power and so on. So we have several of those tools. Yeah.
Thank you, sir. So there's a question. To say it is she's asking, are we in the VLSI or USLI era?
Yes, yeah, we have actually moved to ULSI, but generally, we just talk about VLSI. I mean, maybe in the academic domain, I mean, maybe VLSI is outdated, but it's these terminologies are just for our convenience. Yes. Yeah.
Thank you, sir. Yeah, thank you so much, sir.
Okay.
It was very informative session. So you have enlightened us with many concepts such as semiconductor design complexities, criticality of electronic design automation, the electronic design automation for physical design, and you have enlightened us with many research of challenges in the chip design domain, how machine learning can be applied in VLSI, and also on the power aspects in chip design.
Yeah.
Thank you, sir, for such a wonderful and informative presentation.
Yeah.
We will now be breaking for lunch, and I request all the presenters to log in at 1 p.m. through the Google Meet link sent for the paper presentation tracks. Okay, please check your tracks and log in at the specified times. So I repeat, now we will be breaking for lunch, and we would be rejoining at 1 p.m. All the presenters are requested to rejoin at 1 p.m. using the paper presentation tracks, using the Google Meet link sent for the paper presentation tracks. Please check your tracks and log in. Thank you.
So Imtiaz sir, 1 o'clock onwards, we will start session through Google Meet. This one, Google Meet. Hello, Imtiaz sir. Hello, Weber sir. Anna ma'am. Rajashri ma'am. Hello, I'm audible. Okay, fine. I got a message. Okay, thank you, sir. So 1 o'clock we'll start through Google Meet, and tomorrow again we will use Zoom link for the keynote speech and all. Okay, sir. So now we are